Hello and welcome to the Delta Change Data Feed Talk in Data and AI Summit 2021. In today's talk, we're going to cover what is the data capture challenges in the Lakehouse, how change data feed in the Lakehouse is working, how do we capture the changes, how do we process them, and Raul will show you a notebook how this works in it.
Right. Hello, everyone. I'm Jose. I've been a software engineer at Databricks for a couple of years now. I'm a committer for two open source projects, Delta Lake and Apache Spark. And yeah, I'm a professional database enthusiast and amateur cooking enthusiast.
Hello, everyone. I'm Rahul Mahadev. I'm a software engineer at Databricks. I've been a Delta Lake committer for the past 2 years. And I got my master's in computer science from the University of Illinois.
And my name is Itai Weiss. I'm a lead solutions architect in Databricks. I've been working with Apache Spark since version 1.6, and I consulted numerous firms across financials, insurance tech, pharma, and many more. So Delta Change Feed is part of the Delta Lake open source. The Delta Lake open source provides you an open source data format that is reliable, based on ACID, so protects that whenever you commit the data, you will be able to read exactly the same data. It improves the data warehouse performance on the data lake, has advanced security features, and of course, an open source format. In this talk, we're going to first look at what are the challenges we faced today when we're trying to look at changes in the data across Delta versions. So today, in the big data domain, we have a lot of data. Changes are coming in frequently, sometimes a lot of them at once, sometimes only a few of them. But in many cases, we just want to process the newest changes. What has been changed since the last time we processed the data? It was doable to do it based on Delta time travel. We could have queried the current version and the previous version, do a full outer join, find out what has been changed, in other words, what has been updated or what has been deleted. In parallel, we can run the inserts and do all of these in Spark. But this was complicated. So we would like to offer you a new way. How do we solve it? So Jose will show you soon how this works under the hood, but really what we give you now is a very simple option to read only the change data from a specific version or a specific timestamp to a version or a timestamp, which are optional. You will avoid full table scans. You don't have to worry about the logic. You know that every time you do it, you'll always get all the changes. And you will, of course, reduce compute and memory. And you can use it to improve your ETL pipelines. You can use it in batch and streaming. You can use it from your BI or dashboards, and you can use it to meet regulatory needs to identify exactly what has been changed and when. Delta Change Data Feed works on Delta and only on Delta. So if you have other change data capture tools, as known as CDC, these will capture other external data sources outside of the Lakehouse. But really, you will be able to use Change Data Feed, as we call it CDF, between your bronze, silver layer, and gold. Bronze, silver, and gold layers, and identify these changes and propagate them forward or to your downstream application. How does it work? We're starting with the original table. We now have 3 records, A1 primary key, A2 primary key, and A3 primary key. We're adding a change data block. A2 is updated, B2 is now being changed to Z2, A3 is being deleted, and B4 is being inserted. The end state table will show you A1, A2 updated, and A4, A3 will be deleted, but now you can get a new data frame, which is based on the change data feed output. In this case, we get 4 records. A2 has a pre-image. You can see that column B has a B2, the old value. A2 as well has another record for a post-image. You can see that column B has now the new value, Z2. Both of them will have the time and the delta version. A3 has been deleted. You will get the full record with all the columns with the change type delete, of course, the time and the version as well. And B4 will have change type insert with, again, the full record columns, the change time and the version. As you can notice, A1 does not exist there. How do you consume it? So you consume it both in stream or in batch. In the upper layer, we can look at the streaming consumption. On the left, at 12 p.m., we have the same change block we looked at in the previous slide, and we'll just consume it one after the other. On 12:08, we're getting a new record, A5, which is an insert, and we'll just pull it and append it to the next layer, as we always do. At 12.10.10, this is where complexity and more interesting solution is coming in. We got a new record A6, but immediately after, we got an update. So as you can see in the string, we have 3 records. One of them is from version 4, and the last 2 are from version 5. In this case, our streaming solution will have to find what is the latest commit version and process only the last one, because this is what we're really interested in, and we'll avoid duplication downstream. The batch consumption is even easier. At 12, we just process the 4 records, as we talked about before. 12.10, we just get 2 new inserts, we push them. At 12.20, we get an update, we can process an update, update the record downstream, and complete our story. And now Jose is going to explain to us how this magic works underneath.
All right, so under the hood for Delta in general, changes are stored as ordered atomic units called commits. And you can see an example of this on the side of the slide here. Each commit is represented by a numbered JSON file containing what are called add actions and remove actions. And these represent tables where these represent files where the rows within these files are added to or removed from the table in that version. So with change data feed, in addition to those files which represent the current state of the table, we also have change data feed files, and the contents of these files are the rows containing the change events within that table. So there's a couple different uses that change data feed could be applied to. It's useful within our bronze, silver, gold architecture. You can improve the performance of Delta tables by processing only the data changes between your initial bronze ingestion layer and your gold business layer. You can use it for materialized views to create up-to-date views based on the changes as they come in without having to rewrite the entire contents every time. You can transmit changes to downstream systems effectively, again, without having to output the full state of the Delta table every time. And you can use it for audit trail cases, both in terms of seeing what has changed in this particular version, and in terms of if you have some particular row, how has that evolved over time? What changes have people made to it, and when did they make those changes? Right. So as with any software system, there's a lot of great things about change data feed, but there are trade-offs involved. So we do have to talk about where it is and isn't an appropriate thing to use. For use cases that include a lot of updates and deletes, where a small fraction of the records in the table are updated within each batch, change data feed is a great choice for that scenario, because it greatly reduces the amount of work you have to do to read the changes from the table, at the cost of a minor increase in writing out this change data. On the other hand, for a table for workloads where the changes are primarily append only, or when most of the records in a table are being updated in each batch, change data feed can start to get more expensive to produce and to read. So in those cases, it may not be the appropriate tool. Similarly, if you have data that you're receiving from external sources in a CDC format, change data feed is often a natural way to express that, because it kind of maintains the same structure of the events. Whereas if you're receiving data in the form of destructive loads, which is a term that refers to when you get a new batch of data and it's meant to completely replace what was there before. In that scenario, the change data feed is kind of not a natural way to express such a workload, and you would typically want to use a normal batch scan in that scenario. Right. So how do you start using change data feed? The first step is to enable it for a table. And there's a table level configuration. Table properties is the term for it within Spark SQL, where you can turn it on, and then after you turn it on, your table will start producing a change data feed that you can scan from. There's also a Spark cluster level configuration that you can use to turn on change data feed for all Delta tables that are created within your cluster. And then once you've initialized it, once you've configured your table to produce a change data feed, you can query it using this table changes function that allows you to see the changes in the feed, either in a particular version range or within a particular range of times. And then once you do that, the result of the table changes method is just a normal Spark SQL data frame. So you can transform it, you can split it, you can display it, or you can store it into another table for use in later downstream processing. And yeah, here you can see a short example of how the table changes function can be used within a notebook. Yeah, you can see that the user here has queried the table changes for this silver table from versions 2 to version 4, ordered by the timestamp of the commit, and then the result of that query is just a data frame showing the row data for each of the change events, and then the metadata indicating what type of change event is this, and when did it happen, what commit version, and when in wall clock time did it happen. All right, so yeah, next up we have Rahul, who will be showing us a practical demo of how change data feed can be used within Databricks notebooks.
In this demo, let's explore the change data feed feature of Delta Lake and see how it can be used to keep derived tables in sync. In this example, we have two tables, so let's call them silver and gold. The silver table tracks the number of people vaccinated and available doses for every country, and gold table tracks the vaccination rate for the country. And first, let's start off by creating these tables, silver and gold. As you can see here, we have like the country along with the number of people vaccinated and available doses. So this is our silver table. And let's quickly create our gold table. So we have the same rows in the same number of rows in the gold table, but we have a different column called vaccination rate, which is derived from the columns in the silver table. Now, to propagate any future updates, deletes, and merges on the silver table to the gold table, let's enable change data feed on the table. It's as simple as using the order table command for enabling change data feed. So let's just run it. And now any future updates and merges should generate a change data feed on the silver table. So let's try this out by running an update and merge on the silver table. So here we ran an update where we're just setting, for one country, we're just setting the number of vaccinated to a new value. And we also ran an upsert where the new data frame contained new rows, 2 new rows, as well as an existing row with updated values. So this completed. So let's see how the silver table looks like now. So we went from 5 rows to 7 rows. So the 2 rows were added and the 2 other rows were updated. And the first step of propagating these changes is actually to read the change data feed. And to do that, it's as simple as using the function called table changes. And as a parameter to this function, we pass in the table name along with the starting and ending commit versions between which we want the change data feed. So here we're going to pass the table name for the silver table, and we're going to pass in the starting and ending version. So we did 2 updates from
from version 2. So let's see if that works. So as you can see here, we get the existing data rows for the table, along with some additional metadata columns as well, which indicates what type of change it was. So for the pure inserts, we have the change type column indicating that it was an insert. But for updates, we have 2 rows, the pre-image and the post-image, with the pre-image containing the old values and the post-image containing the new values. Now, let's use this change data field to actually update the goal table. So we are going to be using the merge command to do this. And what's different here is for the source table of the merge, we will be using the change data feed. So we use the table changes and we filter out the pre-image here for this use case because we only care about the actual value of the final actual value of the row rather than what the values were before. And we have the clauses again. When the rows match, we update the column vaccination rate, and when the rows don't match, we actually insert a new column. Let me quickly run the merge command and see if that actually updated the goal table. As you can see, we have 2 new rows for the goal table and updated values as well for the other row. So we saw here how in a batch mode, how we can use table changes to actually keep 2 tables in sync. Now, to do this in a more automated manner, let's say we wanted to set up a stream from the silver table and ingest all the incremental changes into the gold table. That is possible as well. And let's actually run like a stream and see how that can be done. So here we have the first step where we actually read the change data feed from the silver table. What's different here is we just need to provide additional parameter called read change feed to the streaming query. And here let's provide the starting version as latest because we already ingested some changes using the batch API. So for the future changes is what we need to ingest. So let's provide the starting version as latest. And again, let's filter out the change type because we don't really care about the pre-image here as well. And the second step here is to define a method that can be used for each batch. In this method, like it's similar to what we did earlier. We're doing a merge for each batch, and similarly, we have like when we see matched rows, we update the existing rows in the goal table, and when we don't see matched rows, we insert like new values into the goal table. Now, let's actually run the stream to write out these changes into the goal table. And I've provided the for each batch method here. And here I'm going to give a processing time of 2 seconds. And let me start the stream. So the stream has been started. And now let us do updates on the silver table. So we have, similar to what we had before, we have an upsert. Let's run it. As you can see, this seems to have been processed by the stream. Let's actually see if the silver table and gold table affect the changes. So now the silver table has 9 rows. We have the updated rows as well. And let's see if these actually made it into the gold table. As you can see, the goal table is updated by our stream as well. And in this tutorial, we saw how to use batch APIs and the streaming APIs for the change data feed feature of Delta Lake. Thank you.
Thanks, Raul. Really good demo. Now we all know how to use change data feed in SQL and Python and process the changes downstream. Please fill up your feedback and let us know how was the session, what you enjoyed, and what we can do better. So we'll be able to serve you better next year. Thank you for joining the session. Goodbye.